The Big Bang Theory at its heart is rather simple idea. The universe started out very small and then started to expand. This video is all about the expansion, but is it slowing down or speeding up? In 1998, two teams of scientists discovered that the universe was itself speeding up. Okay. I may have just given you the answer to this video, but let's carry on and figure out why and how the universe is expanding. This discovery revealed that what astronomers can directly detect only makes up 5% of the total mass and energy in the universe. Invisible dark matter makes up another 24%, while the rest is a mysterious phenomenon simply known as dark energy. The year after the Big Bang was hypothesized, Edwin Hubble found evidence of the expanding universe, when he showed the galaxies are moving away from Earth and the ones that are further away were moving faster. These objects not only blast away from each other through space, but space itself was growing in size and moving the matter with it. The galaxies were not only moving away from Earth, they were expanding away from everywhere all at once. Subsequent observations have helped astronomers to tell the history of the expanding universe. In 1964 the discovery was made of the cosmic microwave background. This is a cold glow left over from the Big Bang. This shows that the universe has been expanding for approximately 13.8 billion years. Surveys of large-scale structure of the universe have since revealed billions of galaxies are clustered together around vast empty voids. These large-scale structures that we see in the universe, such as filaments of galaxies, correspond to minute ripples that we see in the cosmic microwave background. However, the future of the universe is rather uncertain. It was unknown whether it would expand forever, or one day collapse under its own gravity. The expansion of the universe is assumed to be slowing down, due to the force of gravity. Measuring the deceleration should reveal the ultimate fate of the universe. However, when measured, the cosmic expansion is found to be accelerating. This acceleration is due to a previously unknown force that works against gravity. This is now known to be dark energy. Throughout the 20th century, cosmologists assumed that the rate of expansion was slowing down. Following rapid initial expansion, gravity would start decelerating the universe. It seemed like there were two main possibilities for the fate of the universe. If the universe was heavy enough, its gravity would eventually slow the expansion to stop, and then begin to pull matter back together in a cataclysmic big crunch. This is a kind of Big Bang in reverse. The second possibility was that the universe was too light to stop the expansion, which would therefore continue forever, but gradually slow down. This process would result in a heat death, where material of the universe have broken up, becoming infinitely dispersed, and all the particles cease to interact in any way whatsoever. In measurement of the deceleration of the universe's expansion would tell cosmologists which future possibility the universe was heading for. By the mid-1990s, two programs well underway to measure the rate of expansion of the universe. These two projects considered merging, but they had rather different ideas about how to proceed, so they opted instead for a healthy rivalry. Both projects were using the discovery made by the Supernova Survey, and this was carried out in Chile between 1989 and 1995. The survey found the Type 1a supernova could be used as standard candles. This means that supernova, a certain type of supernova, can be used to measure distances across space. A standard candle is an object of known brightness, so its apparent magnitude, the brightness as seen from Earth, shows exactly how far away it is. A Type 1a supernova is a little different than the standard supernova. A standard supernova forms when a large star runs out of fuel and explodes. A Type 1a supernova forms in a binary star system, in which a pair of stars orbits each other. One of the stars is a giant star and the other is a white dwarf. The white dwarf gravitational pull steals the material from the giant because it is more dense and therefore has a larger gravitational pull, The material then accretes on the surface of the white dwarf until it's grown to be 1.3 solar masses. At this point the temperature and pressure are so much that the star ignites and explodes. This creates an object that is billions of times brighter than our Sun. Both surveys use the observatory in Chile to find these Type 1a supernova. The plan was not simply to find the positions of the supernova, they wanted to find the distance should be used by Keck telescope in Hawaii, to take the spectra of each explosion, and this gave its redshift. This is the lengthening of spectra that the light has undergone, so therefore the brightness or magnitude of each star can get its distance, and this could be billions of light years. Well, its redshift indicated its relative speed to Earth, and this is caused by the expansion of the universe. The teams were aiming to measure the rate at which the universe was changing. The rate of the expansion as indicated by distant objects was expected to be decreasing. However, when the teams looked beyond 5 billion light-years, the expansion of the universe was not slowing down. It was speeding up. This result was first thought to be an error, but successive checks showed that it wasn't, and both teams discovered the very same thing. In 1998, the teams went public with their findings, and the results shook the scientific world. Using Einstein's equations of general relativity, they have found that these results appeared to give the universe a sort of negative mass. In other words, it appeared a kind of anti-gravitational force was pushing matter apart. This source of energy was named dark energy because, well, it was a complete mystery. They theorized that if dark energy continues to grow and in the future it may push the universe apart, and it would disperse all of the galaxies so that eventually, they will be too far away to be seen from Earth. Although I doubt Earth would exist at this time of the universe, eventually it may scatter the stars within the Milky Way galaxy. Even the Sun and the planets, if they still exist, would not be safe from dark energy, and then finally the particles and atoms would also be scattered, resulting in a form of heat death. This is dubbed a Big Rip. The universe relies on the critical value in the average density. This can give us a good clues to the future of the universe. The critical value is estimated to be the equivalent to the 5 protons per cubic meter, so if the average density of the universe is below a certain critical value, it should be closed and end in a big crunch. If the density is equal to the critical density, the universe's geometry will be flat and the universe ought to carry on into the future neither expanding nor contracting, and if the density is above a critical value, the universe should be open and expand forever to eventually end in a heat death. Observations suggest that the universe's expansion is accelerating due to this mysterious dark energy. Dark energy may also indicate that the apparent acceleration seen is because we are inside a region with less matter than anywhere else in the universe. This is a distinct possibility. It may also be showing that Einstein's theory of gravity is incorrect of the largest of scales. Dark energy may also be explained by a mathematical device Einstein created in 1917 called the cosmological constant. Einstein used this as a value that would counteract the pull of gravity, and would make the universe a static and very unchanging place. However, when we use Einstein's equation, it shows that the universe can only be dynamic, meaning that it cannot expand or contract. Einstein dropped this constant from his theories, calling it a mistake. The value of the cosmological constant is set to match the energy contained in a vacuum, and this was assumed to be zero. However, in modern times we know that even a vacuum contains virtual particles. These exist for a Planck time. Dark energy may match this sort of idea, a form of energy that arises from virtual particles, and these virtual particles may create a sort of negative pressure that may pull space apart. This may represent a non-zero value for the cosmological constant. The expansion of the universe has not always been accelerating. There was a time when gravity and other forces pulled matter together. However, once the universe became big and empty, the effects of dark energy appeared to become the most dominant force in the universe. It may be that a different force takes over in the future, or it might be the dark energy effects continue to grow. One suggestion or theory, as you may call it, is that the universe will get to a state where it will start to rip itself apart. These risks will be so powerful that dark energy will tear apart space-time itself, and this can create a singularity. And could this singularity be the creation of the next Big Bang? And could that Big Bang just be in a sequence of Big Bangs? Who knows? And to be honest, I'm not too sure. Whoever know the answer to that question, but maybe that's just another topic for another video. So I hope you enjoy the video on dark energy, expansion of the universe and the other bits and bobs as well. And as always, if you enjoyed the video you can click the like button, and if you want to support channel you can click subscribe. Thank you for watching and have a lovely day.